how your kids will inherit it, your spouse.
If I have it.
Marry me and take on my debt. So what we'll do is we'll finish 9.3, and then when we look at review stuff, test review stuff, then we'll look at other questions and homework and things of that nature. But, let's see. Yeah, so next class period, we've got an exam. Chapter 8 and 9. Hmm?
Well,
Yeah, comes quick. Okay, so we were talking about separable differential equations. There's actually this example and an implicit form example left. But someone asked, so this is kind of an aside, it's not in our notes, but similar to what showed up on the quiz, you had y prime of t was y times e to the t, and you were given an initial condition, y of 0 is -1. So we had a similar example, and we didn't have a initial condition that was negative. So we would solve this normally, and then when we get to our explicit solution, well, we'll just wait till we get there. But we've got a separable differential equation with y, sorry, 1 over y prime on one side, and e to the t on the other. And then when we integrate both sides with respect to t, we have 1 over y dy equals antiderivative e to the t dt. So similar to the one we had where we had antiderivative here and natural log, excuse me, absolute value of y, and e to the t plus c. And then we exponentiated both sides to get absolute value of y is e to the power of e to the t plus c. And so from here, you could say that that's just e to the t power times e to the c, which e to the c is another constant. I don't know that that's absolutely necessary, but we can certainly do that. So in our example, we said, well, why was this exponential? But yeah, so exponentials are always positive. But when we look at this like a general solution, it's kind of like the positive and the negative are absorbed into this constant. Because if a is positive here, if that constant's positive, then you just have some exponential function. But if a is negative, then we have that exponential function down here where it's always negative. So when we have a y value of -1, that means our exponential has to come out to be a negative number, which means that that constant has to be negative. That's the only way those exponentials would output a negative number, because it has to have a negative in front of it. So we say, well, working with the absolute value of y, again, we don't want to call this y because our initial condition says that y is negative. Okay, so we're just going to plug in our initial condition here. Y is -1 when t was 0. So we're going to work with this one over here. We have a times e to the power of e to the 0th power. So we have 1 is equal to a times e, which means that our constant that we called a is 1 over e. Is everybody okay with that? I think that's traditional approach. But since the initial condition is describing the y value being negative, when we put this a just based off of this discussion here, or this note here, whatever, that if we have our a being positive as we solve for it, then our exponential isn't going to be negative like it should be for the initial condition, right? So you just have to recognize that and make a negative. So from here, we're going to just say that y, or y of t, more specifically, is equal to negative 1 over e. So we're going to intentionally make our a negative so that it matches up with the initial condition. And then that's what we would do in a situation like that. Does that make sense? So that's you'll have something similar to that on your quiz, question number 10. Because otherwise, like I said, if we put a in as it is 1 over e, then you're not going to satisfy that initial condition, because it'll come out to be 1 and not negative 1.
How do we go from, so initially it was e to the et times ec, so e to any arbitrary constant, no matter what it is, can't be a negative number. So how do we justify having a negative number once we substitute e to the c for a?
Yeah, so like from here, this,
Yeah, like we change the range of that function, supposedly, as we go from e to the c, we go from calling it e to the c to a. So how can we justify that step?
well, it's again, it's just based on the initial condition. Like if we look at these general solutions, sometimes they're misleading. With general solutions, if that didn't have an initial condition attached to it at all, then just saying that we have a constant times e to the t is totally fine. But so like the issue then is, all right, well, if e to any constant is always positive, and then we write it as this a, where a could be either positive or negative, how can we justify that? And we're justifying it because it's based on the initial condition. Like that constant would have to be negative for that function to output negative values.
Although you still have the absolute value of y, so even if it can only be positive, we can just distribute that absolute value to the other side as plus or minus, which defines two different equations, one of which has a negative constant.
Right, yeah, so this absolute value of y, we could say y equals to a e to the t, where then it's implied that a could be positive or negative.
Okay.
Yeah.
That makes sense.
Okay. So the ones that have initial conditions, you do have to be a little bit more careful. Most of the ones that we look at, though, aren't really tricky in any way. They're usually pretty straightforward, but that one's a little less straightforward, I guess. Okay. Any other questions on that? Okay, so we'll go back to this example. So why don't y'all take about 5 minutes and solve this. Again, we've got an initial condition, so we shouldn't have arbitrary constants left. So separate, and remember at this point when we integrate with respect to x, that our y prime is just dy over dx. And we have that times this other dx. So those things things divide out. And so, you know, like we've seen a couple of different ways, like u of t, u of x, y of x, y of t. You know, these separable ones, whatever variable is prime, you want that other variable like the y or the u with the u prime or the y prime. So that's how you know you can separate it. And then this is just this. So we have, again, natural log absolute value of y, antiderivative of cosine. So you can also work with this form here. This form is implicit, because we haven't actually solved for y, but it's implied what y is, I guess. At this point, you could plug in your initial conditions of y being 3 and x being 0. Let's go ahead and solve absolute value of y is e to the power. Remember, exponentiating both sides, so it has to be e to the sine x plus c power. Kind of like in that last one we just looked at, you could rewrite that as e to the sine x times e to the c, or a times e to the sine x. Here our initial condition was y is positive, y of 0 is 3. So we could at this point say, well, you know, that constant a or y can be just written like this. Oops, just kidding. E to the sine. So we have 3 equals a times e to the sine of 0. So that tells us a is 3. If you plugged in your initial condition here with the implicit solution, you would have came up with the constant was the natural log of 3. So either way you approached it, you would still end up with that the function y of t is 3 times e to the sine x. So like if this constant were ln 3, you solve for it the same way, get ln 3. Then when you exponentiate both sides, it's e to the sine x plus ln 3 for y. And then we just rewrite that. It's e to the sine x times e to the ln 3, which is 3, and then we get 3 sine x from that. So you can work with the implicit form as well, which the next example is going to have us doing that. Anyone have any questions about that problem? So this says solutions in implicit form. Solve the initial value problem, leave the solution in implicit form. It means that we're not going to solve completely for u. Leave the solution in implicit form and use a graphing software to plot the solution. If the solution describes more than one function, be sure to indicate which function corresponds to the solution. So we have initial condition here, u of x equals to, or u of pi rather equals pi over 2. And we're going to look at, for a moment, just look at u prime as 1 over sine u times cosine of x over 2. So we see that there's many u values, infinitely many u values in which that differential equation's undefined, right? That differential equation's not defined for any value of u that's an integer multiple of pi, 0, pi, et cetera, and then the negative direction as well. So we'll sort of like hash all of that out as we look through the solution. The other thing that's going to help us eliminate all of the infinitely many places where it's undefined is the initial condition. But for now, we're just going to solve this and then come back to where it's undefined. Multiply both sides by sign so that we have the u's together. So it's separated, u's together, other variable on the other side. We differentiate with respect to x here, or sorry, anti-differentiate with respect to x. And so what do we get? What's the left-hand side? Integral antiderivative of sine u, u prime dx would be negative cosine u. Antiderivative of cosine of x over 2.
2 sine x over 2.
2 sine x over 2.
Plus c.
Yeah, plus our constant. So that's, that's our implicit solution. We haven't fully solved for y, or sorry, for u. You could say it's negative 2 sine, cosine of u is negative 2 sine plus another different constant. But this is our implicit solution. So it says graph, which we need a graphing software to do that. So we'll do we're going to pretend our u is a y just because of this software. 2 sine x over 2. Well, I guess, we could have, so depending on, we've got to find our constant. Depending on what our constant is, we have different solutions. So as we change that constant, so we've got to figure out what our constant is.
It's pretty sick.
Yeah. So we'll figure out what our constant is from the implicit solution as well. So we have u of pi equals to pi over 2. In other words, when x is pi, u is pi over 2. So we have negative cosine of u, already forgot, pi over 2. Negative cosine of pi over 2 is 2 sine pi over 2. X is pi plus c. So we have negative cosine pi over 2, sine of pi over 2. So we have 0 equals 2 plus c, or c is negative 2. So let's write our completed implicit solution down. Negative cosine of u equals 2 sine x over 2 minus 2. That's our implicit that's what we're, initially that's what we're looking at, but then we look at the initial condition and see, where does that initial condition put us through all of this?
It's like an optical illusion.
Yeah.
It's kind of hurting my eyes.
That'll just be solid red if we zoom down. So the initial condition was x is pi, u is pi over 2. So if x is pi, 3.14, so it's somewhere in here, right? Pi over 2, somewhere in here. We can plot that point. So there's our initial condition. It puts us on this ellipse or whatever that is. So we're not concerned with any of that other stuff. We're just concerned with what's happening right there because of our initial condition. Yeah, so then then it says use the graphing software to plot. If the solution describes more than one function, be sure to indicate which function corresponds to the solution. So this isn't a function right here. So then we've got to go back up and say, well, all of this solution is coming from the fact that we have this as our differential equation. So we said our original differential equation is not defined when u is in pi. But now that we have a representation of our solution, we don't have to worry about, for instance, when u is equal to, u is equal to 0 is here. That's not showing up. So that's our u equals to 0 line, right? And then u equals to negative pi, negative 2 pi, et cetera, all that's above and below. We're only focusing on this one right here. So we only need to consider for our initial condition and our solution, our differential equation was only undefined when u is equal to 0. Does that make sense? So that's u equals to 0 is that axis. We know this function is not defined. If we can go to the graph, it might not show or say, but we could go there on the graph and say, well what is that? Let me get rid of this. I mean, I don't know if it'll actually say, but we can certainly try. So it won't even tell me if there's a point there or not. Graphically, it looks like there's a point there, but analytically, our original differential equation is not defined at 0. Oh, sorry, that was x, I think. Sine u. Is undefined. When u is equal to 0. On that line. Clearly, just graphically, there's not an asymptotic behavior here nor here, right? So that, just by inspection, we might say, well, there's probably holes right there on those 2 points. Right? If the function's not defined, we definitely don't have those concrete points. Bear with me. Any questions? Okay. We'll sort of hash it out in a second, but this implicit form is easy enough to solve for y. So we'll let me copy this and paste it here. We'll solve for y so we can see explicitly what are we looking at. Let me just take this now. So that's our explicit solution. Now we're just seeing, like, explicitly it's just the top half of that weird ellipse or whatever that is, right? So those are the points that we should be able to come up with. So let's get rid of that. We're still sticking with this for the time being. I think we have enough room to keep going. So undefined when u equals to 0. So going back to our implicit solution, cosine of u, let me do this, cosine of u, undefined when u is equal to 0, because we want to figure out, you know, all of these horizontals those are all of our u values. We know that it's undefined here. We want to find this value and this value. So we need to say, all right, well, when u is 0, it's undefined. Well, what are my x values that come out of that? So our implicit solution, we're going to use that to solve for x. Whatever it was. 2 sine minus 2. And so that's how we'll end up with those x values. That x value and that x value. Okay, so we've got our -1 plus 2. And that's what our divided by 2, that's what our sine of x over 2 is going to be. So when's the sine equal to half? What angles does the sine equal to a half at?
Pi over 6.
Pi over 6 and 5 pi over 6. Okay. So, you know, if you have a hard time with that, just it's kind of like you're making a substitution. When does the sine of w equal to a half? When w is equal to pi over 6 and 5 pi over 6, et cetera, and then et cetera in the other direction. So if that's the sine of w, our w is x over 2, right? So then you can just make that replacement. Our w was x over 2. Multiply those by 2 in order to get what x is equal to. 2 pi over 6, 5 times 2. 5 pi over 6 times 2. So in other words, when u is 0, we have our x value of pi over 3, giving us a u value of 0, and we have an x value of 5 pi over 3, giving us a u value of 0. So when we say the original, when we said the original differential equation was undefined when u is equal to 0, we now know exactly what points the function was undefined, or the solution was undefined at those 2 points. And again, if we go to the explicit solution, we can see those points come out here. So explicitly we get a little bit more detail when we look at the graph. Yeah, let's see here. So remember initially we said, all right, well, it's all of those ellipses, but then our initial condition put us on this ellipse right here. I don't know that they're actually, but it kind of looks like it. And then when we figure out, well, the function's undefined when u is 0, that gives us the point pi over 3 for x and 5 pi over 3 for x. Really, we have our solution described here, but our solution graphically is that the top half of that curve. We know that these are holes, so our graphical solution would be this thing. That's at pi over 3, and this is 5 pi over 3. So that's what our solution would look like. It's not the bottom half of the round thing. Do y'all have any questions about that? So something like that can't be on the test because you can't graph it. So. You might have 1 or 2 homework questions where you have to do something like that. Okay. I believe that's it for 9.3 if y'all don't have any questions. All right, I did post this first page already. Just again a breakdown of the types of questions on the exam. These basic antiderivatives, you should like secant, natural log of x. Those are the ones that you should know quickly without really having to do anything. Things like integral of secant, integral of tangent, integral of cotangent, those all came up with trig substitutions fairly common, or were fairly common with trig substitutions. The other one for like inverse sine, inverse tangent, you should know those pretty quickly as well. So basic antiderivatives just means ones you should probably know without having to do a whole lot of thinking. The 2 integration by parts, one definite, one indefinite. There's 2 trig integrals, one with powers of sine and cosine, other with powers of secant and tangent. The 2 trig substitutions, 2 to 3 partial fractions. One question will have you just set up. So like it'll just say, hey, here's this function. What would it look like if you were going to start the process of partial fractions? You don't actually have to like solve for A, B, C, D, E, F, G, and all that stuff. So one of them is just rewriting. The other 2 are integrations. 2 improper. One question from initial value problems in 9.1 and one separable from 9.3. So that's the exam. Something from integration by parts that I at least wanted to mention, because I don't know that we explicitly looked at it, was like evaluate the antiderivative of inverse sine of x. So sometimes in chapter 6 we avoided inverse trig functions because we couldn't find the antiderivative. With integration by parts, we can find the antiderivative. Integration by parts. We have have to choose our u and our dv. So what should we choose u as? Inverse sine of x. So that means we have to take the derivative for du. What's the derivative of inverse sine?
1 minus x squared.
Yeah, 1 over square root 1 minus x squared. So if we have this as our u, then our dv has to be dx, which means v, the antiderivative of dv, is equal to x. Okay, so the original integral or antiderivative is u times v minus the integral of v du. Okay, so it should be the integral of integral of v du should be easier or comparable to the original. It's kind of hard to compare the two, right? Can we find the antiderivative of x over the square root of 1 minus x squared? Yeah, how would we do that? You could try a trig substitution or a u substitution. Substitution?
1 minus x squared.
1 minus x squared, all right. So we're going to let u be 1 minus x squared. Du, well, we're trying to account for the x, so we'll have minus 1/2 du is x dx, right? So u substitution totally works. U substitutions are easier than trig substitutions. A trig substitution would work as well. Alright, so I'm gonna write here x inverse sine x minus the integral. We have our minus 1/2 du here for our x dx, and then we have 1 over the square root of u, or u to the negative 1/2. And we'll call this positive. So that's pretty much done. We can find the antiderivative of the inverse trig functions using integration by parts. So you have x inverse sine x what do we get here? Plus 1/2 u plus 1, so u to the 1/2 times 2 plus constant. 2 1/2, and then resub u was 1 minus x squared. So antiderivative here is then x inverse sine of x plus 1 minus x squared to the 1/2 plus c. So any of the other inverse trig functions, very similar process. Do you have any questions on that? Yeah, so most of the ones on the test do say find the antiderivative or evaluate by using partial fractions or whatever method. There might be one or two where no method is specified, so most of them are though. Okay. Do y'all have other questions you want to look at or talk about? I didn't bring anything with me, so I was hoping y'all had questions. I guess not. I can go get the
You did a
textbook.
good job.
Huh?
That means you did a good job.
Yeah.
So, how about we get like the inverse cosine?
Inverse cosine. So I don't know. The only difference with inverse cosine is the derivative here is negative, right? So you'll have the derivative of inverse cosine that's -1. This will be positive. Use substitution. You'll have a -1/2. You'll have a negative, so this will be negative. This will be x inverse cosine minus square root 1 minus x squared. I think, something similar. Just
Because
because
like I forgot like about like the inverse cosine.
the derivative.
Yeah, for the derivative. I
Yeah.
forgot.
So if you know the derivative for inverse sine, inverse tangent, and inverse secant, then you know the other cofunctions derivatives, because with the inverse trig functions, they're exactly opposites of each other. They're just off by a negative. So like if you know the derivative of inverse sine is this, you know the derivative of the inverse cosine is this. Derivative of inverse tangent, derivative of inverse tangent, inverse cotangent rather, inverse tangent, inverse cotangent. Inverse secant, inverse cosecant is just the negative of that. Yeah.
Could we go over 8.9, number 12?
All right, third time's a charm. Find the volume described by the solid of revolution, or state that it does not exist. The region bounded by this function, the x-axis from 0 to infinity, revolved around the y-axis. So what does that function look like?
We have 2 pi times the integral from 0 to infinity, or d limits the inverse infinity of x times x plus 2 to the negative 7.
anything. I just didn't catch all of it. 2 pi integral from 0 to infinity.
That's it.
Okay.
Disk
So,
Shell
Yeah, yeah.
word for it.
Yeah, so we can.
Warsher.
Oh, okay. Awesome. I don't know. Just about as good as it's gonna get, I think.
It's only bounded by the x-axis. And the y-axis.
All right. So there's our function. I guess I should have captured the 0 there. But anyways, this crosses the axis somewhere up here. Finding this area. It's bound by the x-axis, the function on this interval, and we're revolving that around the y-axis. So you've got two choices. We can say, all right, well, do I want to slice parallel to the axis of revolution, or do I want to slice perpendicular to the axis of revolution? So which one? Then we say, all right, well, is the top function minus the bottom function easier to compute, or is the right function minus the left function easier to compute and integrate, right? So we know the top function is this thing here, minus 0. Okay. If we wanted to do it this way, we have to integrate with respect to y, which means we need to solve that function for y, or so for x rather. So you could do that, but you would have, be a little bit more complicated maybe. I think both ways you could totally do those, washer or the disk, or the shell method rather. So if we're going to slice parallel to the axis of revolution, to the y-axis, then we're using the shell method. And the shells are 2 times pi times r times h. Remember, the height of the shell is just as you see it, right? That's the height of my shell. It's top minus bottom. Here's the height. The radius is the distance from from your slice to the axis of revolution. That's our radius. Right minus left, and that's some x value, x minus 0. So radius. Everybody okay with that? Okay. So that's our, we'll write it down here, that's our setup. This integral. All right, and how are we going to integrate that? By parts, use substitution. Right. You know, sometimes you would see this function as x over x plus 2 to the positive 7th, right? So we probably wouldn't do a partial fraction on that. If that were like to the 2nd power, you know, partial fraction could work, 3rd power. I don't know. It's just a repeated linear. You have a over x plus 2, b over x plus 2 squared, c over x plus 2 cubed, right? This is a little more involved. So you've got a couple of choices to find the antiderivative here.
If you use a u sub, you won't get an x dx.
What do you mean?
Because if you put u being x plus 2, that is du just equal to dx.
Yeah. Yeah, you just solve that. If u is x plus 2, then du is dx. But if u is x plus 2, u minus 2 is x, right? So what I would recommend, like I said, with these things, find the antiderivative first. If you make a substitution, then resubstitute. You can certainly say, well, since u is x plus 2, my lower bound is 2. My upper bound is still infinity. Still works the same, but that's what I would recommend. This is the antiderivative of u minus 2 times u to the negative 7. So we're just integrating powers of u at that point. Let's write it. This doesn't matter, but we'll have u to the negative 5 over negative 5. Sorry about this. Have plus 2 over 6. Oh, I'll write that as 1/3. Plus 2 over 6 u to the negative 6. And then we've got a plus c, find the antiderivative, but it's a definite integral, so that will go away. Resubstitute x plus 2. So there's our antiderivative in terms of x. Does anyone have questions on that? So put that in place. So just keep that in mind. We've got to fix our bounds. Fix our bounds in terms of a limit. So we have this is 2 pi times the limit. Our upper bound is the issue, whatever you call that. We've been sticking with b approaching infinity of this thing. Which is this thing. Oh, I don't know why I wrote x plus 5 over there. Still just x plus 2. Okay, so there's the antiderivative evaluated from 0 to b. And, you know, maybe since we're gonna plug b in and allow b to go to infinity, you can think of this as 1/5 times x plus 2 to the 5th. Right? And the same thing over here, this is 1/3 of x plus 2 to the 6th on bottom. So as, well, I guess we'll just plug this in. Plug in our b. Plug in our b. And then we plug in our 0. So minus 1/5 times 1/2 to the 5th plus 1/3 to the 6th. Oops.
Do you want those exact numbers?
Yeah. Should, I mean, you've got, I don't, what do you have? I mean, they're pretty large numbers, but they're still finite.
I was asking if you want me to give them to you.
Oh. Yeah, sure. I don't wanna think about it.
I'll leave it alone.
Okay, so 2 pi limit as b approaches infinity. Is everybody alright with that? With where we're at? Any questions? Okay, first pair, I guess, as b goes to infinity, what happens to those? They both approach 0. Something over, -1 over a very large number, 1 over a very large number. Okay, so what it was 1 over 5 times 32.
160.
160. So that's 1 over 160. And then 2 to the 6 times 3.
384.
160 minus 1 over 160 minus 1 over 384 equals something times 2 pi. What is that? Pi? Do you know that?
Oh
Should
no,
we
I
have
left
one?
it as like pi over 80 plus pi over 96.
Okay, no, whatever. There's your answer. Some variance to that. But it is finite. You have a finite area. Or finite volume.
Is it cool to leave that like that and not try and find common denominators and waste a bunch of time on a test?
Yeah. I don't usually have problems with numbers like that anyways, so
Oh.
I think at that point, yeah, it's fine. Like, I'm not terribly concerned with your arithmetic. I'm sure your calculus is on point. Yeah. All right. How about we take a break? I can go get a textbook too. I want to work out other stuff.
Last regular one. Yeah, that one.
Plus 81.
Yeah, that one, I think I
Oh,
filled
I
up
always skip
about
the
2 or
last
3
problem of
sheets
each
of paper
homework
on
and
that
then the day of
beforehand.
study
Yeah,
I
I
go back
spent
to
about
those problems.
45 minutes on it.
Because I know they're
and
hard,
then,
the hardest
at
ones
some
are
point
going
I had the
to
integral of secant cubed. I'm like, yeah,
I would just.
I know how to do it.
What I did with one of these is like when I had like the x to the 4th or x to the 3rd or whatever, I just put like constant to the 3rd or constant to the 4th instead of like multiplying it out. And then like as you go along, it will all cancel. So you'll go from having like an 8 to the 4th.
Jen's boss.
He has a beard now?
Sometimes.
Oh, no, okay. It's
Depends on the problem.
It's another guy.
Like,
Yeah,
if you like multiply it
Yeah,
all
so it's not
out
weird.
and like
Yeah,
do
like, for
everything, you're
calculus.
gonna like.
Yeah,
maybe
I
not
did,
count what?
I did that too, and you end up getting like 1 over
Oh, is
the
it
square root of
Stephen Wolf?
whatever number
Does it
it
work?
is. Yeah, that's the one. That's the one.
Have,
Wear glasses.
no idea.
Yeah,
I don't
that
either.
was-
I know who you're talking
That is
about, but I don't know the
Oh,
name.
yeah.
That. His hairline receding.
Yeah.
Jeez, Will.
Turned out the last regular one was the last
That's
one.
not where I was going with that. I wasn't trying to get to that.
So I should probably.
Yeah.
That one.
That was kind of funny though.
Now you use everything.
It looks like you could use like a salad.
It's a good prop, it's just.
So something like that, yeah, I think that's pretty, it's pretty advanced as far as like techniques for integration. You know, definitely not things that complex on the exam, so. This is in 8.4, which was trig substitution. So if the instructions on the exam were evaluate using trig substitution, we first have to get it in a form that is applicable to trig substitution, where we have a difference or sum of squares under the square root. So in order to do that, we complete the square on x squared minus 2x plus 37. So complete the square. On x squared minus 2x plus 37. So we scoot that over. We take half of -2 and square that. We add that to the x's and subtract it over here. Okay, so now we have the sum of squares, but it's under the radical. But that's at least a little bit better than what we started off with. At least starting to take shape of ones we've, you know, commonly recognized as trig sub problems. All right. So.
Did you do the same thing to the top with that one? Did you take it to the x minus 1 squared as well?
Yeah.
You would, okay.
We can write the top as x minus 1 squared, because otherwise we would say, well, all right, the bottom looks like squares if we had a u substitution. You know, we did one in class where we had something similar and we didn't do a u substitution. We said let x minus 1 over 6 equal to, you know, tangent or sine, whatever it was. Things got a little messy because we had to say, well, what's the top? You know, add 1 to the top, subtract 1 to the top. So we did that in class. But yeah, this quantity here, the x squared minus 2x plus 1, is also up top. So if we rewrote that, we kind of have the same quantity here that we do under the radical. And then that way when we say, okay, we're gonna let u be x minus 1, then we have just this straight substitution. So you could do a trig substitution from here, it's just, it requires a little bit more manipulation. So u is gonna be x minus 1. Dx is du. And so that's it just turns into that. Difference of squares on the bottom, so, you know, however you handle it, textbook just says make a trig substitution, let, we're gonna use sine, cosine, or tangent for our substitution. Tangent. Because we have tangent squared plus something is secant squared. But the textbook would say, let u equal to 6 tangent theta, and then you factor out later. The way we're doing it is we're just factoring out first. So we're factoring a 36 out of u squared and the 36. So under the radical, so we get that out completely as 1/6. And then we have the square root of u over 6 quantity squared plus 1. So the only reason I choose to do that is because our Pythagorean identities with our trig functions rather are like sine squared equals to 1 minus cosine or 1 plus tangent squared. So it always has those 1s in there. That way maybe we can make a little bit more of a stronger connection to those trig identities. But anyhow, that's our substitution. We're going to let u over 6 be tangent theta. And again, the u substitution I don't think was entirely necessary, but it does kind of clean things up a bit for us. So u over 6 is tangent. That means du, well, we should probably, yeah. So du is 6 secant squared theta d theta. And then our u squared is going to be what?
36 tangent squared.
Yeah. Oops. So much for that. 36 tangent squared theta. We have 1/6 u squared over the square root of tangent squared, so tangent theta squared plus 1 times du, which is 6 secant squared theta d theta. Okay. Any questions? We've got 6 times 6 again divided by, or 36 times 6 divided by 6, 36. Antiderivative here, what do we've got on the bottom? All of that's the square root of secant squared, or just secant. So one of those goes away. We've got our 36 tangent squared times secant. So we've got powers of tangent and secant, but when we split off a secant tangent, it doesn't, you just have a tangent to account for, you can't account for it. So it's like if it were tangent squared left over after we split off a secant and a tangent, like if this were tangent cubed times secant, then you could go through the procedures we talked about in 8.3 and it would work. So unfortunately, you can't sort of split that up according to those methods, but we can rewrite tangent squared using the Pythagorean identity as secant squared minus minus 1. And then, so that's where things get kind of, well, more messy. So we have integral of secant cubed minus secant. And so, I don't know, the homework says something about reduction formula for secant cubed. We actually integrated secant cubed in class, where we had a 12 secant cubed. But integrating secant cubed, you have to split it up, secant squared times secant. Then you integrate by parts. And it's one of those integration by parts integrals to where you have to solve for the integral itself, like the e to the x sine x type thing.
We got the, is that the one we add to?
Yeah. So yeah, you have to add it. So it's like if you just keep going in circles because you have the same representation over and over again. So do we want to do that? Do you want to see that again?
Yeah.
Okay. So let's rewrite this then. A couple of things will be combined because we can find the antiderivative of secant, right? It's just the secant cube that's the issue. So I'm going to just see how much paper we've used. So let's just do that on the next page and we'll come back to this page. Okay. So integration by parts, u and dv. What do we want our u to be? Secant. Remember the acronym or the whatever the mnemonic, the LIATE says let u be the leftmost function. And basically what that's saying sort of implicitly is we could also say that's the equivalent of making dv the largest part of the integrand that we know how to take the antiderivative of. Okay, so we can certainly take the derivative of secant squared, but thinking about dv, we have to take the antiderivative of dv, and we know the antiderivative of secant squared. So that's the largest, I guess, largest chunk of the integrand that we can find the antiderivative of. So du is derivative of secant. So secant tangent d theta, and v is the antiderivative of secant squared. We have already used u for our u substitution, so I'm just going to call this u bar and v bar. We don't have to use the v bar because we haven't used v yet, but just for technicalities. And then we have that integral, leave some space here, is u times v. Minus the integral of v du. Does that look familiar? That's what got us here in the first place, right? So that, we've already handled that here. That's just secant cubed minus the integral of secant cubed minus secant. Okay, so we have secant theta tangent theta minus the integral. Remember, so well, I guess there's a couple ways to think of it, but this whole thing just turns into secant cubed minus secant. So usually you're probably not writing out, you know, what that integral is equal to, because it usually just simplifies. But in problems like this, as soon as you notice the same integral that you started with, that's when it's conducive to write the whole equation out. Because we're gonna end up solving for that integral. So we have the, this is the antiderivative of secant cubed. With a minus here, and then, because we have the minus, the antiderivative distributing to both. Antiderivative plus the antiderivative of secant. And so it's, you know, kind of getting rid of the parentheses and looking at it as two separate integrals. We have secant theta tangent theta, and that's still equal to secant, the integral of secant cubed. Okay. So then we're solving for that integral. We add 1 to both sides so that we have 2 of these over here. And then, you know, we'll divide this side by 1/2, just not to have to write it again. Secant tangent theta, that's gone. What's the integral of secant? Natural log,
Secant theta plus tan theta.
absolute value of secant plus tangent.
I guess just the hardest part is really just remembering that step.
Yeah.
Like, once you see it repeating, especially when you're doing electric functions, that secant squared theta, that part just to add it to the other side. That's,
Yeah.
because you're like, okay, hold on. What's the next step for me?
Right,
Like-
yeah, yeah, so it's crucial, it's absolutely crucial when you're doing these things that repeat, that you recognize that, because these things that repeat are gonna keep repeating. You're gonna break secant down cubed, secant cubed down again, have the same thing, and then you'll have like, you know, 10 of these things that we've already expressed. Okay, so this is the, well, then we'll put this 1/2 over here, right? We have 1/2 over here, which means we're getting rid of this 2 because we divided through by that 2. Okay.
Tricks up.
Yeah, right. Yeah, here's your test. It's one question. Okay, so then we're gonna put this stuff in place of what we had over here. Yeah, we're like halfway done, I think. Maybe a little more. It's ridiculous.
We're almost here. So I'm
Okay.
supposed to
So we'll have this, just so we're not, I don't know, just so we don't get our constants messed up. Okay. We know both of these now. It's 36. Antiderivative of secant cubed, it was 1/2 secant theta tangent theta. What was it, minus? No, it's plus. Plus 1/2 natural log absolute value of secant plus tangent.
So we were more than halfway.
Huh?
We were more than
Yeah,
halfway.
maybe so. I was being a pessimist. Minus 36 times, again, antiderivative of secant. Remember this minus 36 is times both of these. Or we could have just factored out the 1/2. Then that was 18. But anyways, just so we're clear, we've got those constants and those constants. Okay, so there we go. Secant cubed integral minus secant's integral. So, distribute 36, we'll have 18 secant theta, tangent theta, plus another 18 of these, which we have a negative 36 of these as well. So we can then combine like terms.
We get it. You're good.
Well, somebody looking at the notes at home.
Yeah, you said that never happens, and I purposely liked it so you knew that it did happen.
You purposely what?
I liked your video, so
Oh,
that
okay.
I was watching it.
Okay. Always turn the comments off. These comments on YouTube videos are brutal.
Yeah.
All right. So then we'll combine these two things. Right. Combine those two. And then after this, all we've got to do is convert back into X.
Cool.
That's it.
You gotta convert back to you and convert back to X.
Yeah, right.
Do we care about the plus here, or do we just wait till the end?
Yeah, I'm just gonna wait till the end to add one grandiose constant. There's already enough to keep track of. Let's write it like, well, okay, one more step. All right. We're good. So then, go back to we made two substitutions. So from here, we can say, well, tangent of theta was u over 6, but u was x minus 1. So tangent of theta is really just x minus 1 over 6, isn't it? X minus 1 over 6. Wait.
It'd be 6 times
X minus 1 over 6, because x minus 1 is u.
Oh. Yeah.
Tangent of theta is x minus 1 over 6.
X minus 1 is opposite. 6 is adjacent.
So our trig sub was u over 6 is tangent of theta, but our u was x minus 1. So you could do it separately, right? You get theta, the representation for secant tangent and secant plus tangent in terms of u, and then resubstitute u, or we could just do it at once. Doesn't really matter. So sometimes people don't draw the triangle, which is fine if you know how it's constructed. But I recommend drawing the triangle just so it's less things you have to keep track of in your head. It's kind of a bummer if you get it all this way and then you mess this up and then you resubstitute the wrong thing. Okay. All right, so opposite is x minus 1, adjacent 6, hypotenuse would be
Square root of x minus 1 squared plus 6.
yeah, if you see as you've done all these, that other side is just that part of your integrand. That was what we had under the radical before we made our new substitution.
Squared gives 2x plus 37.
Yeah. Okay. So we've got then 18 times secant times tangent. So secant of our theta would be what?
6 over, no, root of x minus 1 squared plus 36
Yeah.
over 6.
This root all over 6. Let's just write that as, we can expand it, it doesn't really matter. Okay, so that's our perfect square, our sum of squares under the radical. Secant theta, tangent theta, we already know what that is, so times tangent theta, x minus 1 over 6. And then we're subtracting off natural log of secant plus tangent. I guess I needed bigger parentheses. All of that's times 18. So there's your answer, plus C.
X times x minus 1 times square root of x squared minus 2x plus 37 over 2 minus natural log of square root of x squared minus 2x plus 37 plus x minus 1 over 6 times 18, so we 3 times all that instead of over 6 plus c.
Yeah. So we could certainly simplify this a little bit, right? You've got an 18 over 36 here. You've got an 18 times this natural log. The natural log, we can write this as the root plus x minus 1 all over 6. And then we can say it's the natural log of the root plus x minus 1 minus the natural log of 1 over 6
Or we could just show
times.
18 inside the natural log and raise it all to the 18th power. So
Right.
get rid of the absolute values. Just even power.
Yeah, so there's a lot of options we could go through from here to rewrite this. The 18 times this thing right here can be put up as the power. You know, so there's multiple ways one could go from here. So I would say leave it like this, because I think most everyone that did this problem would definitely end up there if you did everything correctly. The way we simplify might be different. Because again, this constant, there's ultimately a constant here with this natural log absolute value that can get absorbed into this constant as well. But we won't worry about that. Okay, so that's a decent problem. It's definitely hefty to work through, but there's a lot of there's a couple of concepts at least involved in doing that. So, anybody have any other questions on that?
No, but you got to use up the class period.
Yeah.
So let's do the square root of tangent next.
Square root of what?
Tangent.
Square root of tangent? I don't know that that's.
It is.
I've seen a
Yeah.
video where someone does it, they only use techniques from calculus 2, it takes them like half an hour, but it can be done.
Oh,
Just calc
interesting.
2.
Yeah, I was watching a video on Feynman's technique for integration, where it's like Leibniz's rule is what it's called, where you can take partial derivatives under the, or distribute a partial derivative through the integral. It's where you and so it ends up being like a integration by parts, a partial fractions problem, and sort of this initial value differential equation that you have to solve. So it's
Awesome.
pretty wicked.
I was gonna say, can I come to you for help with gradients?
Grades?
Gradients.
Oh, gradients.
we're starting them in physics, and like, you should know this, but not everyone knows this, but we're gonna be doing this.
Oh, yeah. I hear that's kind of common. Like, oh, you probably haven't seen this. Here's what it is. All right, let's go.
Oh my.
Yeah, so any other questions you have? The exam? So like I said, if you're initially using the the help tools on MyMathLab, you know, I don't think that's detrimental unless you're overusing it. And if you have found yourself overusing it, then go back through your homeworks and just look at those problems and try to remember how you solved it. That way you're practicing like recalling that particular skill. So when you see something on the exam and it may or may not say use this technique, you can say, oh, hey, the degree of the numerator is larger than the degree of the denominator. I definitely know I need to do long division here first, or you know, whatever it is. But practice recalling those strategies on your own. And then hopefully at some point when you're studying, you're not looking at your notes, you're not looking at help me solve this at all. I recommend that for like your first run through on the quiz, because they're difficult, but if you run through the quiz blindly with no help, then you for sure know where your deficiencies are. Like, I don't recognize integrals of this form when I have to trig substitute, or whatever it is. At some point, hopefully you're studying without your notes, because that's the real test of what you know and what you don't know. Okay, so that's my speech on study skills.
Or you can take the class again.
Yeah, or you can take the class again.
Look,
I'd love to see all of y'all again, but hopefully not in Caltech.
Hurt my pockets here.
Okay. Well, so we call it a wrap? Yeah. Okay, I'll hang out if you have other questions, but we'll officially end.